Welcome to this webinar on F6G. So today we are reunited to encourage discussion, research, and technological cooperation on the promising subject of F6G, which has received a limited spotlight until now. So for your information, this webinar is recorded and will be broadcasted on video platforms. About the program, we will have an overview of F6G around the world and review the use cases and user needs where F6G can make a significant contribution. Also, we will review the key enabling technologies and scientific challenges for F6G. At the end of the webinar, there will be a session of question and answer. So, of course, feel free to ask your question. You can also ask your question directly in the chat, and all of you can have your the answer. So we will begin now with the first presentation of ETSC ESG. So it's the vision, fixed network, and evolution toward F6G.
Hello, my name is Frank Effenberger, and today I'd like to introduce to you the Fixed 5G initiative and how it enables digital transformation in many industries. So if we compare wireless and wireline technology progression over time in the wireless domain, there have been several generations, very well-defined generations, that were defined the standards technology in ITU-T and the wireless technology and roadmap in 3GPP and GSMA. In the fixed world, there's been sort of a missing part of that equation that there's been ITU standards, of course, to define the basic technologies, but there hasn't been the generation definition, and that's really what the ETSI Fixed 5G initiative is meant to fulfill. So if we look at the fixed network, in our way of looking at it, we're up to the 5th generation of fixed networks, just to sort of to match the similar progression in the wireless domain. And so, of course, as the network has evolved over time, of course, first we had voice, then the internet occurred, and then video onto digital media occurred, and then more and more. And so fixed 5G is really sort of talking about a 10 gigabit capable network, 10 gigabit PON, generally 200 gigabits per wavelength in the core network. And so by accelerating all of the bandwidths, we can achieve much more services over the same common network. And the characteristics or dimensions of the Fixed 5G initiative are three. One is to consider enhanced broadband, so basically higher speeds. There's the guaranteed reliable experience, which is about reducing latency, not only of the actual transmission, but latency of setting up connections and things of that nature, managing the network. And then full fiber connection, which has to do with expanding the network to touch more endpoints. So why ETSI? So ETSI, of course, is a very well-established standards organization centered in the European Union. And it's been the home of these groups that have helped define the wireless generations. And so it seemed only natural that we could do the same thing for fixed networks that has been done for wireless networks. And it's an open organization. Anyone is welcome to join. And in fact, we encourage participation in this ISG as well as any others. So if we look at sort of where is Fixed 5G and how does it interrelate with the other standards groups, we have a sort of a constellation of different organizations that have developed technologies that are used in the fixed network. So IEEE, ITU, IETF on the internet side, Broadband Forum, ETSI, OIF. And so really what we're missing there is sort of the thing that pulls all of those things together. So if you could go to the next animation. So that's really what Fixed 5G is aiming to do, to try to pull all of these different disparate technology standards together into one cohesive plan. And it's planning of generations, but also looking at use cases, different ways to use the technologies in new ways, and then ultimately looking at, do we have all the tools we need in order to meet those use cases? And indeed, you can identify gaps. Then we can try to work to fill those gaps with additional solutions. So really what it's about is trying to expand the fiber network. At this point, fiber is clearly the sort of end game for all fixed networks. The access is now becoming fiberized. There's around 1 billion users that are served by fiber in the access right now, and that's growing over time. And so we're expanding that. We've made a good progress on fiber to the home. We now are looking to extend that to fiber into the home, so that's fiber to the room, or fiber to the business, or fiber to the office. A lot of different ways that we can expand the fiber network even broader. And then basically we'll be reducing the fiber and user distance. So it used to be that we were always talking about the last mile. Now we're talking about the last 100 meters or even the last 10 meters. So it's definitely getting much closer to the user. So some of the contributions of the fixed 5G effort, there have been work on architecture, so the consideration of defining different planes of functionality in the network. So there's an underlay plane, which is the actual physical network, the actual fibers and switches and other things that do the actual work. But then there's a service plane, a virtualized kind of plane, that you can define all kinds of different connections and service types on that basic underlay plane. And then, of course, there's the management and control plane that stands above that allows you to control all of that. And to some degree, there's additional notion of autonomous control, so that the network could watch the user's data and interpret that and understand what does that user need in terms of service quality. And then there's also work on use cases. This shows a sort of a snapshot of some of the use cases that are being studied. There's quite a number of them, so it's really you can see all kinds of different applications for fiber networks, both access and transport, to try to broaden the appeal of fiber to everything. So we look at one of these use cases just as a way of example. There's the passive optical LAN. So in a typical campus kind of situation where you would be connecting a bunch of workers' computers, you'd use a bunch of switches and then interconnect all of these with point-to-point connections. And this generally requires a staff of trained engineers to actually manage the network, physically make all of these different connections and maintain it. So if we can use the access network and extend that into the office, now it becomes an operator-managed solution. So now the company can just connect its employees' computers directly to the network, and then the operator will manage that service for them. So it allows them to eliminate the need for all of those trained engineers that go around and keep the network running. So it's really aiming to increase the efficiency of the network. Another use case is a PON for industrial manufacturing. So in the case of industrial settings, it has some very unique characteristics. Typically, you're talking about things like machine control, machine vision to inspect product, and then actual robotic machines to actually make actions on the product. And all of those things require very high reliability, very good compatibility with all of the different schemes, low latency, of course, ease of deployment, and security, of course, is very important as well. And a lot of these optical access networks provide a very good solution for that. And indeed, even at the very lowest physical layer, because it's using fiber instead of wire, there are even less issues, for example, with corrosion or explosion hazard. All of those things are improved using fiber. Another use case is the enhanced optical transport network. This is basically looking at what you need to do to build a network between data centers. Generally, the traffic between data centers is very bursty, that they need to download a huge amount of data from one center to another and do it very quickly. That's basically what that requires, is you to set up connections on a dedicated basis so that we can download all this data in a very fast way. And having the highest capacity in the network, highest speed per wavelength will of course increase the capacity. That will reduce latency and also improve reliability with all the technology we have with protection switching, with mesh routing and so forth. We can make sure that no matter what happens in the network, we can get the data from A to B. And so if we look at the evolution of the fixed 5G, we see in a set of drivers that are pushing us, there's sort of the digitization or cloudification of applications as sort of one major trend, and there's sort of an illustration of some of those drivers there. And then there's network infrastructure improvements, so basically making the network better just as a means of improving its quality. And so, as I said, fixed 5G had these 3 dimensions that were its focus. Now, the fixed 5G advanced, which is just a thing that's in working now, is expanding that. So, of course, we're still improving those 3 existing dimensions, the faster, the wider, and the smarter. But we're also adding new dimensions. So things like a quicker, so things to support industrial applications or tactile internet, so very, very low latency capabilities. More awareness, so visualization and sensing of the network, so the network becomes more of a sensor rather than just a pure transport, and greener. So of course the reduction of carbon emissions is very important, and the network can play a role, very big role in that regard as well. So that's a very important new aspect to consider. All right, so thank you.
So after this vision toward F6G, now I invite Fabienne Saliou, a researcher engineer at Orange, to join stage. And she will present F6G for access network, the future 50G PON.
Yes, thank you very much for the introduction. So hello everyone. So today I would like to talk about the future of 50G PON for future access network in the context of F6G. So I share this presentation with my colleagues at Orange in Lannion in France. So first, just to give a brief overview of what was presented before by Frank. So we see an evolution of the generation of fixed networks, optical networks, from 5G, F5G to F6G. And typically, we are going to move from a world with gigabit services to a world with 10 gigabit per services when we talk about evolution from F5G and to F5G advanced. And since this webinar wants to talk about F6G, so we will try in this presentation to look at what could be the F6G. So for us, it could mean that it is 10 to 100 gigabit everywhere in terms of services, and it is seen as something that could arrive after 2030 in the timeline. So. As Frank said also, it is really motivated by the fact that we see arriving fiber to everywhere for really an unlimited future in terms of connectivity. So we need to make the fixed access a future-proof network. And for that, we are talking about bringing fiber closer to the usage and to the users. So we know already today that we have fiber to the home, and we are also now having great deployments with fiber to the room, typically for connectivity in homes, but also in small and medium enterprises. We have fiber to the room that can be a solution also to deliver fiber closer to the usage. And another opportunity to have this fiber evolution would be to also deploy fiber in enterprises for fiber to the desk, fiber to the office, and also fiber to the factory for fiber to the machines to enhance the automated network in factories. So this means that we will have more and more users connected to fibers, but also shorter distances to cover with this fiber at the end of the network. And we will increase dramatically the number of connections. We talk about 3 times more connections for fiber to the room, and even up to 100 more connections point for smart cities typically. But now that I presented this context about F5G, F6G evolution, I want to go back to the fixed access networks that I want to focus on today. So fixed access networks, optical net access networks, for us at Orange, it means 2 types of connectivity, either point-to-multipoint connectivity or point-to-point connectivity. The last one, point-to-point, is more dedicated to fiber to the antenna or fiber to the office, with a dedicated point-to-point fiber from the OLT to the antenna or to the office. But for point-to-point connectivity, so typically a PON network, we have one point from the OLT connected via optical splitters to multiple users, which are the ONUs here. And this is typically done for FTTH today for the residential market. And for that, I will talk now about the evolution we see with these two technology, PON and point-to-point connectivity, that has been seen with regard to the different generation of fixed networks. So from F1G to F5G, so this is typical applications and technologies that could be identified to support this evolution. So today we are now, let's say, between F4G, F5G, depending on where we are deploying. So either we have GPON technologies that supports services with typically 1 gigabit per second in the home. And this is based on specifications that are done in the ITUT. And this brings Wi-Fi connectivity in the home, which is based on Wi-Fi 5 or Wi-Fi 6 today. But these standards exist since 2006, and there's been already some evolutions that are possible with bringing more bitrate in the home. So typically with 10 gigabit per second services. And this is supported by the technology that was specified in 2017. It is XGS-PON, so symmetrical 10 gig PON technology. So this, let's say, has been well identified already and it is deployed. But now if we want to look a bit further, so we can identify here, this is our proposal from Orange. This is not discussed already at sea, but this is proposed for F5G Advanced that following XGS-PON, we will have another PON technology, which is the 50 gig PON. And this is in the goal to support 10 gigabit per second services or even higher bit rates. If we talk about point-to-point connectivity, we can even reach 100 gigabit per second services. In terms of use cases, this is identified to support industrial IoT, autonomous vehicles, and smart cities. And we see here really the first arrival of fiber to everything, or fiber to everywhere, with fiber to the room and fiber to to the home also. In terms of timeline, we can see that we try to put here a commercial available solutions for 50 gig PON or 100 gig point-to-point in around 2027 for the volume deployments here for these technologies. And looking a bit further, so this is like really our imagination, and but we think that this is the evolution that is going to happen for F6G. For F6G, so 6th generation of fixed networks. In that case, we are talking about having 100 gig services and even higher bit rates. So sometimes we talk about terabit services that will be required for typically mobile connectivity, for Industry 4.0, for augmented reality also, autonomous transportation and e-health. So in that case, we need to support 100 gig and even higher bit rates. And there is discussions now in the ITUT to have very high-speed PON solutions. And it's still very early in the discussions, but we are talking to have more than 100 gigabit per second line rate with a PON. So typically 100 gig PON is being discussed there. In terms of timeline, we see these new technologies arriving after 2030. So we're still very early to discuss about these technologies in detail today. So that's why today I wanted to focus on the evolution of F4G to F5G Advanced. So typically here the evolution from GPON to 50 gig PON. So first, let's look at this evolution. So Orange has reached 60 million of households that are connected to FTTH worldwide. And this includes 31 million in France. And what we have done for this connectivity is mainly based on GPON technology. The GPON technology is able to distribute fiber to the users with a line rate of 2.5 gigabit per second in the downstream and 1.25 gigabit per second in the upstream. And we are now going to deploy also the new technology, which is XGS-PON, which offers 10 gigabit per second symmetrical bit rate. And how we do that? We will do that because both of the technologies have been defined in terms of wavelength plan, in terms of specifications, to provide a coexistence on the same optical distribution network that we have deployed already. So this optical distribution network is based on fiber and optical splitters. So typically distribute 1 to 64 users from a single transceiver at the OLT. And we provide here this upgrade to XGS-PON with a multi-point module, which is a single transceiver based on SFP+, which we call combo transceivers sometimes. And this includes both technology of GPON and XGS-PON in the same transceiver. So from this transceiver, then we distribute the GPON and XGS-PON to all the users, so XGS-PON and GPON. On the user side, it is not based on the pluggable transceiver. It is really the technology, optical technology is based on BOSA that are based on the board of the gateways at the user premises. So now let's look at the further evolution. So for 50G PON, there's been it is the latest standard that has been released in the ITU-T in 2021, and there's been also some progress that was made this year to provide 50G PON symmetrical specifications. And so here we see typically that we need to reach a high optical budget as high as 29 dB for the class N1 and 32 dB for the class C+. And we need to support, of course, the TDM, TDMA protocol. So burst mode for the upstream is a really a challenge when we talk about 50 gigabit per second in the upstream here. And a generic challenge for this is really at 50 gigabit per second to find the low-cost optical components to support the specification that was proposed here, and to be able to find a solution for 50 gig PON that will be, let's say, that will be enough to be deployed on our networks. So we have done some first evaluations of prototypes of this 50 gig PON. So it is coming on the market, and today it is with asymmetrical bit rate, so 50 gig downstream and 25 gig upstream. And today, with this technology, it is not possible to have a coexistence with the latest one, which was XGS-PON. So I will explain that in more details now. This is related to the 50 gig wavelength plan. So at first it was proposed like this, and we see that the 50 gig PON wavelength band that was optional for the upstream are overlapping either with GPON ones or either with XGS upstream one. So it means that we couldn't have the 50 gig PON with GPON, or we couldn't have the 50 gig PON with XGS-PON. So then when we saw that, so we are left, in terms of operators, we are left with 4 choices. So either we can deploy 50 gig PON only on specific fiber infrastructure. So when there is a green field, we could start to deploy only 50 gig PON, but this will require to invest again in fiber plants. So this is something we really need to avoid because it represents a high cost for operators to deploy fiber. Or another solution would be to replace all the XGS-PON with 50 gig PON to coexist with GPON only. But it is not likely that we will give up, let's say, on the most recent technology for going forward to 50 gig PON. So at first, let's say, there was more enthusiasm to replace all the GPON by 50 gig PON to coexist with XGS-PON only. So this was promoted by the Asian operators to bring volume for these options also in terms of wavelengths for the upstream. And lately there's been more discussions to try to provide triple coexistence, and for that we needed to review the wavelength plan. And this is a solution that was preferred by us also at Orange. So here we see the volumes of the evolution expected in terms of volume for GPON, XGS-PON, and 50G PON technology. And we see that in 27, when the 50G PON will arrive with volume, we will still have a lot of GPON on the network. So that's why here we really need to have a triple coexistence. We need to have a new solution that will support both GPON, XGS-PON, and 50G PON on the same fiber plant. So with this discussion being made, there's been a review of the wavelength plan for the upstream options. And now there is a new upstream option for triple coexistence, which is here, which is 1286 plus minus 2 nanometers. And this is allowing to have the three technologies to work together on the same fiber plants. But it is so narrow now that maybe it will require more advanced filters and more advanced transmitters at the ONU sites in terms of temperature control and so on. So now that this has been said, we are waiting also for progress now from the vendors to include this triple coexistence in their roadmap. So it is in their roadmap now, and they are going to provide multi-PON modules with the three technologies in the coming years. So that's good news. We can reuse the fiber plant for a smooth migration between 50G PON and the older technologies. But we are still remaining with current challenges for 50G PON. So it is related to the 50G transmission that we want to do with low-cost components. So typically we target to reuse the optics that are offered with the datacom market, which has already a huge volume, and try to adapt that for PON networks. But for that, we need to add some digital signal processing because we are typically limiting the bandwidth of the optical components. So we need somehow to enhance that for having good transmissions. And also we try to avoid to increase too much power consumption and complexity. So with DSP, we try to really base this new technology on low complexity DSP if possible. In terms of upstream, the burst mode is really difficult to be achieved at 50 gigabit per second. This is with regard to the amplifier that is behind the receivers. For burst mode, it's very difficult to achieve this amplifier, and also to recover the clock after bursty traffic. It is also not so easy to do that at 50 gigabits per second. So we are still waiting for some progress in the technology in that way. And another big issue is that so far it is still very difficult to reach high optical budget for 50 gig PON. So we see here on the left, on the right, sorry, that we have deployed our GPON technology with quite high optical budget for some of the users. So typically we are reaching 35 dBs for some of the users. So it's not most of the cases, but we have some of them that are above 28 dB, and we need to connect them, all of them, to the future networks. So that's why we need to reach the class N1, class C+, of course, but also maybe the class D. And for that, we are talking about using extra optical amplifications to achieve this high optical budget. So it is really something that is new in optical access networks. So far, it was only passive optical networks, and we try to keep it that way, adding optical amplifications as boosters or as preamplifiers. And we also would like to reach same performances for any reach of the network. So for the users that are connected at 0 kilometer or at 20 kilometers, it has to be the same performances. So if we look into details into possible implementations of this 50G PON solution, there's many parameters that are left open to the vendors' implementations. So typically, they can choose different emitters, so either EMLs or DMLs, with or without amplification integrated. They can also choose some different receivers. So typically a pin is recommended, or SOA plus pin to achieve high optical budget, or even APD can be considered at each side of the networks. And also the different filters that could be involved there can be also different from different vendors. So it leads to very different implementations, and because of this different choice of optics, also the DSP can be very different in terms of implementation by each vendor. So that's why we think that maybe the physical layer interrupt for this future solution of F6G can be quite challenged, and it is an effort that we will need to do later to try to have interrupt between OLT and ONU from multiple vendors. And for now, if we want to deploy F6G on the field, first things to do, we'll have to include in the test plan that we have the new metrics that are involved with the F6G, so typically the TDEC and so on, and also to specify F6G power meters to support deployments on the field, and to provide a triple coexistence. So this is needed to go with further studies on this new technology. So it's still not available to be deployed yet. And so finally, for this presentation, I wanted to focus very quickly on the F6G technologies. So we are talking about bringing 100 gigabit per second as a service. And for that, ITUT has started discussions with very high-speed PONs. So if you look at this evolution, we see evolution of GPON, XGS PON, and GPON 2 also somewhere, and 25 gig PON, 50 gig PON, and also here is arriving 100 gig PON in 2030, so something like that. So we need to know exactly, is it going to be for 100 gig PON or 200 gig PON? We don't know yet, but this is being discussed now in the ITUT, so we'll get answers in the 5 coming years, I guess. And we see also an evolution related to the fiber infrastructure. So as I said earlier, it is really important to achieve high optical budget and also to bring some flexibility in the optical path. Why we need this is to provide redundancy, because we believe that with so much high bit rate to be transported, we also need to secure the network more. So we need redundancy in the access, which we don't have today. We need also low energy network features and higher speed ratio and longer reach. Typically, we can also consider to allow here for F6G to have new fibers for fiber to everywhere. So it could be a new fiber designs like hollow-core fibers for ultra-low latency services. And last but not least, we also see an evolution in terms of infrastructure. So we are talking about all optical networks now, all photonic networks. So typically we can consider to have an evolution of the OLT system with photonic switching that will help to increase the capacity of the OLT. And also to help to reduce the latency, we can consider some optical bypass of some active equipment. And this is in the framework of the ION Global Forum. So this has been discussed, this concept of all photonic networks now, and also in the European project Octopus. And I want to finish this presentation with a very important matter. So we see that future evolution of networks will be not anymore challenged mainly by the cost or with the technology, but really we have a very important goal is to reduce the CO2 impact of the networks. And for that, Orange has taken some commitments, but not only on Orange, many operators. So they want to reach net zero carbon in 2040. And for that, we think that photonic can help, and photonic technologies and networks, they must demonstrate this global CO2 reduction, not only in terms of direct emissions or energy consumptions, but it is really important to look at that in all the scopes of carbon emissions. So typically here on this graph, I show the real data evolution from scope 1 and 2 from orange group. So we see we have this kind of slope. It's going down very slowly. And on the up, we have the objectives that was taken by the orange group in terms of the three scopes, so scope 1, 2, and 3 objectives. And we see that we should have this kind of slope instead of the blue one, let's say. So we really need to make huge progress to decrease the carbon emissions to support the future networks. So this means we have to make some energy savings to avoid emitting CO2, and also to provide full life cycle assessments and upcycling of the technologies in the networks. So thank you very much for your attention. So if you have questions, please feel free to ask.
Yes, Fabienne, there are two questions for you. One from Jean-Luc Pauleux. Current challenges for 50G PON are the low-cost optics with limited performances. On the detector and respectively laser side, what would you like to improve mainly?
Yes, thank you very much. So typically on the detector side, so now we are seeing an evolution with higher speed APDs. So typically we can see that we have APDs with about 25 gigahertz bandwidth, and that should be sufficient to avoid to use DSP for signals for upstream transmission, for example, at 25 gigabit per second. So this is good news. So what we want what we try to promote at Orange is maybe that for 50G PON, we don't need to have digital signal processing. Maybe analog signal processing could be enough. And for that, we need to select very well the components. So for the emitter side, it is possible to have either DFB or EMLs, or EML plus SOA if you need to reach very high output powers. And it is still challenging, let's say, to integrate these transmitters at the end in transceivers. We need to make sure that we can adapt the driving voltage to the transceiver. So this is, let's say, the remaining challenge that we see on the transceiver side.
So there is also another question. Could you try giving numbers or ratio of improvements expected?
Okay, so for the transmitter part, for example, today what we see is that we need to drive the EMLs or the DFBs with typically something above 1 volt peak peaks, but this is really difficult to integrate then. So we need to be able to reach some driving voltage below 1 volt or below 0.8 volt peak peak. Typically, we need to reach output powers of the transmitters that are from 5 dBm to 11 dBm. So this is also quite high. And from the receiver side, it is also required to reach sensitivities as low as something about minus 23, minus 24 dBm is required for these 50G PON transmissions.
And there is also a question from Sébastien Bigot. So do you expect protocol modification to truly benefit from the new hollow core fibers? Is there no risk that benefits vanish with existing protocols?
I don't know exactly yet what will be the protocols to be used with hollow core fibers. What we see is first to use hollow core fibers really with point-to-point links for very specific networks. So in that case, with the point-to-point links, we are seeing an evolution to support the OMCI, for example, that is involved in PONs to help on the management layer and the control layer of these point-to-point links. But I haven't seen any evolutions really regarding the protocol to be transmitted in these specific fibers yet.
And a last one from François Lelarge. Could 100G PON be based on 56G baud PAM4 components?
So this is still really open in terms of discussions in the very high-speed PON discussions that are going in FSAN in ITU. So we are talking about 100G PON, but maybe also 200G PONs. So far, there's not been any solution that was selected. What we see is that 100G PON based on PAM4 can be quite risky because we may suffer from back reflections, which PAM4 is very sensitive to that. So maybe it's not the best solution for PON networks. So it is really important to have this possibility with point-to-point connectivity because we are not crossing a lot of splitters and so on. But for PON, it is at higher risk to use PAM4 when we talk about 100G.
Thank you. And I have a question for you also. Yes. So concerning the structures of fibers, will there be a significant modification for F6G compared to F5G, or is it the same fiber?
So mainly, in most of the cases, we have deployed fibers since 2006 for fiber to the home, and this fiber will remain on the network for the next 20 years, I guess. So we want to maintain this architecture as much as possible. We don't want to reinvest in fiber everywhere, but we see opportunities to deploy new fibers in upcoming networks. So for fiber to everywhere, there is a lot of fiber still to deploy there, and maybe with specific needs. So we can consider different fibers there. And also for fiber to the antenna, which is really specific in terms of needs for ultra low latency and secure networks. There we can see new fibers also arriving to support low latency and to secure, to provide redundancy with dynamic paths and so on. So we see here, let's say, more evolution in terms of infrastructure, mobile and for fiber to everywhere.
Okay, thank you very much for your answer and for your presentation. So now I invite Gabriel Charlet, Director Optical Communication Technology Lab from Huawei Technology France, to join stage. So he will present F6G, so F6G that imposes challenges and requirements, to network solutions. So Gabriel, it's
thanks,
yours.
Nadia, for the introduction. So I want first to introduce, let's say, the different kind of networks that we have currently. So we have a very long network, like submarine system, with distances in the range of 10,000 kilometers. We have core networks that are dedicated to connect main cities of a country or of a continent with typical distances in the range of 1,000 kilometers. On here, typically, we have some mesh network that are here for redundancy and reliability. We have other kind of networks that are, let's say, metro network, could be ring topology, and that are here to connect, let's say, a different part in a region or a different subpart of a main urban area. And all these kind of network are sharing more similar kind of technologies with wavelength division multiplexing, WDM, and coherent transponders. So that's the kind of network I am working on in my lab at Paris. Okay, so that's the different part we are doing in my lab. We are working on WDM transmission to maximize capacity per fiber, typically by widening optical bandwidths. We are working on optical network, especially to work on digital twin to have a, let's say, a highly optimized network. We are working on optical DSP, so for this coherent DSP, as well as optical component like SOS. But there are other kind of network, let's say, that exist. We have let's say, connection between data centers, like DCI, that could be point-to-point or relatively short distances. Then we have also network, let's say, within the data center, so data center network with short reach distances. Then we have also fiber to the home or PON with distances in the range of 20 kilometers maximum. And here we are using intensity modulation and DI detection. And now we have even fiber to the room, very small network within the home. So when we are talking about optical network on fixed network, we are talking about all these kind of optical network working together. And of course, we have the transition part that are shown by the arrow, but we have also the switching part that is shown by the rectangle or circle. And of course, both have to be connected. So today we're here to talk about F6G, but before to talk about F6G, we could have a quick look of the previous generation. So again, the idea is to try to mimic, let's say, the roadmap that has been done very successfully by wireless people with 2G, 3G, 4G. So if we look back in the past, let's say F1G was in the 90s, let's say with the voice areas. F2Gs was on years 2000 with DSL coming on 10G WDM, and it was the web area. Then F3G was the video area, so around 2005 with VDSL, so higher rates for access, 40G WDM and the networks. F4G starting, let's say, around 2010 with GPON on 1 gig coherent in the core networks. And now we are at F5G, so with 10 GPON coming, and with higher rate for the optical networks, and of course, more and more applications. So let's say F5G is well defined. F6G has still to be defined, and I think we are here to talk about that. But if we are looking at F5G, let's say the goal is really to bring fiber everywhere for everything and to connect everything, and to help us to go for this digital and green transition. And really the vision of F5G is not to look at the technology of one part of the network alone. It's really to have some end-to-end view and look really at the use cases. And of course, on my side, I'm working on a optical system, WDM, long haul, high capacity, but it's just one part and one small part of the whole network. And again, the idea of F5G and F6G that is coming is to, let's say, hear what people will need in the future, and then to think how we could deliver these services end to end. So as I have said before, there's some issue here. So we are working, of course, on transport. So okay, the slide is not really as it should be, but where we have some transponders that are multiplexed, and we transport this transponder over long distances. But of course, we are connected, let's say, to switching elements that could be IP router or Ethernet switches or OTN switches. And let's say to connect the switching element to the transponders, we have typically some small pluggables. It could be, let's say, QSFP form factors on some reaches that could be quite short in the range of, let's say, below 2 kilometers typically. And then we have for the WDM part some bigger transponders that could be either some board or some larger pluggables that could allow to transport the same rate. So, for example, here 400 gigabits, but over longer distances, like 1,000 kilometers or even more. So, of course, we should have some alignment between the rate that we have in the IP and Ethernet switching world and in the WDM world. So 1 gig Ethernet was standardized in 2010 at similar times than 1 gigabit coherent. 400 gigabits has been standardized in 2017, and 4 gigs WDM is coming now. And then what we have seen at usually we have a evolution of rate by a factor of 4. So here the next rate will probably be around 1.6 terabits, even if in the future things could be, let's say, more flexible than what it has been in the past. And of course, having some alignment between WDM rate and the switching rate is something that is good. Even if it's also possible to have, let's say, WDM rate higher than the IP or Ethernet rate, and then we could have some a multiplexing of two, let's say, IP router rates into one WDM transponder. But we have seen in the past that when we have this alignment, like say like the 1 gig generation or the 4 gigabits, it could be even more successful, let's say. So I think it has been mentioned several times before that having a low latency and guaranteed latency or low jitter is something very important. And if we are using some statistical multiplexing switching technologies like IP router on Ethernet switches, it's very challenging to do that. So one option that we are pushing in the optical world and that allow to have this guaranteed latency and low jitter is to use OTN switching. So again, typically here we are showing some application where you could have one user that could use two different kind of services. One that just needs some, let's say, internet services. So we will use some IP technologies, and then you have the ONU, so at the user within the home. Then it will be connected to the OLT in the operator network. And then the signal can go as a standard ways through IP routers all along the route to connect to the internet. But then if we have some specific application, so here the example on the slide is about gaming services where you need low latency, or it could be also, let's say, all the new services that will come with, let's say, augmented reality, virtual realities, mixed realities. We see all the announcements with an headset coming. We could connect at the OLT through some OTN port to have all the transmission through OTN switches that will allow to have a constant latency on a guaranteed bandwidth on jitter. And again, this path that we called OTN Golden Pipe is for high priority services. And that's really something that will enable these new services. So I will not talk long about that, but there are many services that people are talking about that will come in the future. Of course, we have no certainty about which one will be the most successful, but we see now more and more maturity and announcement about say virtual gaming, a new headset, let's say medical aids, production control also in factory or industrial design. On all these new services will require high throughput, low latency, and low jitter. And again, we have to develop the network that will support these new services. So as it was mentioned before, we have F6G that is, let's say, here now with this, let's say, 3 main directions with high throughput, low latency, on the high density. And then F6G Advanced was already defined. And here we want to expand to new directions, be greener, be quicker, and more aware. And when we're talking about F6G, I think it has fully to be built. We have to define it together, and it's still quite open now. So of course we will have to start from F5G and probably to make some evolution from that. So again, that's our role now to define F5G. So what will be the network in 7 to 10 years from now? So if we are looking at optical networks, Fabienne mentioned before the evolution from a GPON that is now, let's say, highly deployed, transition toward 10 GPONs. So again, something like almost 5 to 10 years between one generation and the next one. 50 GPON that will correspond to F5G Advanced. And then we see that between each generation, we have let's say a throughput evolution by a factor of 4, more or less, between GPON and 10 GPON and between 10 GPON and 50 GPON. So we believe that the next generation after 50 GPON may have to aim for 200 gigs PON. So of course it will be very challenging and possibly we may need some disruption. So again, not clear at all that we could continue to use current technologies like IMDD, so intensity modulation, direct detection. So again, nothing is well defined for this 200 GPON, and it's even not clear it will be 200 GPON. But again, having an evolution by a factor of 4 seems what could justify, let's say, for the operators, the new investment for this new generation. So again, the PON generation is something like 8 and 10 years, and we aim to increase the bandwidth by a factor of 4. Now, if we are looking at the WDM transport, so that means with reach of 1,000 kilometers or more. If we look in the past, we have had some successful system working at 1 gigabits with a QPSK modulation. We were able to transport 8 terabits with, let's say, something like 4 terahertz optical amplifiers. A few years back, we were now with 200 gigs generation. I'm mentioning QPSK modulation that allow to go over very long distances, so thousands and several thousands of kilometers. Here we have been able to double the capacity by increasing the optical bandwidth from 4 to 6 terahertz, because when we go to higher rate, we need larger channel spacing. 400 gigs QPSK is coming now. Of course, we need twice wider optical bandwidth. And if we want to double capacity, we will have to use a C and L band, so with 12 terahertz of optical bandwidth to further double capacity. And what come next, let's say for F6G advanced, it's more 800 gigabits with 200 gigahertz channel spacing, probably. And what will come for F6G, maybe targeting 1.6 terabits per transponders. So here we will likely need wider channel spacing, but there are many uncertainty on challenges and probably disruption required. Again, if we want to increase significantly capacity, we may need to go to parallel fibers. Up to now, all WDM systems have been using, let's say, a single fiber, and capacity was going up by having higher rates on higher optical bandwidth. But it will be probably difficult to further expand significantly the bandwidth, even if we could still expand the bandwidth with S-band, for example, but it will just give 50% higher bandwidth. So parallel fiber is a way to scale capacity. We may have also some questions about, let's say, transponder evolutions. When we're looking at baud rate evolution over the past decade, we have seen that the baud rate has increased by a factor of 2 every 5 years, almost. So we're now at 140 gigabaud. 200 gigabaud has been announced and may come relatively soon. Is it possible to continue to even higher baud rate, like 400 gigabaud? Or should we go to a different directions? Like, could it be more lower cost, smaller size, more power efficient if we go with multi-lambda, multi-wavelength transponders? So again, that's a question that we'll have to answer, and I think there is no clear answer now. So I'm now concluding. Okay. So after F6G PON, the access technology may need a major disruption. So we'll go to coherent access. Let's see. Regarding, let's say, transponder scaling for a WDM system, it may also be extremely challenging to continue to increase baud rate. So here also we may need to have a description and possibly going to multi-wavelength transponder. That will be quite different from what we have done in the past 15 years. In the same way, for WDM capacity increased, it may be challenging to continue with single fibers. So should we go to a multi-fiber link? And what will be the implication also on the network? So not only on the transmission system, but also on the ROADM, on the node. And all that may need, let's say, may drive the need for higher integration in WDM network. So to integrate array of amplifiers, array of transponders, let's say, of lasers, modulators. And we see now, let's say, we're talking for now quite a few years about augmented reality, virtual reality, mixed reality applications. And all these applications will require, let's say, larger capacity, lower latency, and also guaranteed bandwidth and jitter. And here, OTN, so which is a switching technology developed by the optical world, is something that could be also key to support these needs. So if now there's any questions, I am here to answer.
Thank you very much, Gabriel, for your presentation. So I have one question for you. How will you manage to develop multi-fiber links in the future?
So typically today in one cable, there are quite often hundreds of fibers that are deployed. So the change is not so much on the fiber that is there, at least for many, for some operators. Some operators are owning cables that have many fibers. On here, the change is more on the optical amplifiers part, and also on the ROADM, how we could integrate in a cost-effective way optical amplifiers, ROADM. And of course, there are other operators that are renting fibers, and this operator may try to go in a different ways and to use as little fibers as possible. So for them, expanding the bandwidth as much as possible to rent less fiber and to pay less could be the way to go for them. So again, we may have different options for the different operators, depending if they are owning the fibers, and if they own the fiber, how many fibers they have available, or if they are renting the fibers.
Okay. Thank you very much. There is one question from François Lelarge. Could SOA be used for improving the link budgets in PON network?
Okay, so I'm not at all an expert about PON network. So I think, yeah, the question would be more to ask to Ernst, but I mean, you may put SOA at the transmitter side. I think here there's little changes. I mean, of course, if you have higher power, you will go to longer distances. If you have a SOA at the receiver side, it may depend also on the optical filters that you may consider. But okay, I'm not an expert of PON network, so I will let other experts answer for that.
Thank you very much. So if there is other questions, of course, there will be also a session of question and answer at the end of the webinar. So feel free to ask any new question to Gabriel in this session. Thank you very much, Gabriel, for your presentation.
Thanks.
So now I would like to invite Sébastien Bigot, Director of IP and optical networking at Nokia Bell Labs France. So to join stage, he will be presenting key enabling technologies for F6G network and system. So the stage is yours, Sébastien.
Thank you. So it will be my pleasure to give you some insight on what in Nokia we believe could be the next generation of access networks. For that, I use some input from colleagues, Joron Mas and René Bonk. And so it's going to be about what kind of technology do we have available and how can they solve the challenges that we have ahead of us and the opportunities. So the way we tend to present that is through the four zeros. Four zeros that we believe are driving trends. First of all, of course, we need to continue to keep up with the growth of capacity. And that comes with having also the need to connect everyone. We don't want anyone to be left unconnected. There's still room left to change the game here. We don't want to be stuck into a given technology, what we call zero limits. Let's open our minds and just select the right approach for the right application scenario. Another trend that is really driving changes also is easing the life of operators by going to zero touch, automate as much as possible the network. And last but not least, maybe the most important, we need to worry about climate change and environmental impact. So we want zero waste and reduce power consumption as much as we can. And we know optics is good at that. We've seen that picture already showing the evolution of PONs over time, BPON, GPON, XGS-PON, and the latest 25G symmetric PON, and then the upcoming 50G PON. Those evolutions have their own reason to appear. Just as a reminder, we started to be very residential. And over time, new application domains started to appear, targeting businesses, targeting offices, targeting the support of 5G, and also new applications. All that are major drivers to make PONs more efficient, more and give them more value. So that, because it's been discussed already, I will skip, but make an emphasis on something that that we have seen recently is the fact that PONs have started to move to a new generation. Nokia is one of the few vendors who have developed the 50G symmetric PON. We've been, I must confess, surprised by its success on the market. But the truth also is that XGS PON has a massive increase. So it means there's a true appetite to move on and continue to expand PONs to make it to give it more capacity. The challenge that we have, and it's also an opportunity, comes sometimes with the diversity of configuration that come on the field. We have a central office where there's an OLT exchanging data with users that are distributed and not as close to the central office as we would like all the time. So that this distribution of comes with a distribution of loss. Distribution of distance comes with distribution of loss. And also, not all operators choose the same split ratio. Essentially, light is sent broadcasted to every user. So the splitting ratio matters. How much in the end photons each and every ONU will receive depends on it. And if you add on top the fact that for a given distance and a given splitting ratio, not everyone is alike because of just statistical variations, then there's an obvious opportunity to think of it statistically. The bottom graph represents what we can estimate would be a distribution of loss in a typical network. And it emphasizes the fact that typically we design the PON for a small minority of the users, those that actually hit the limit. Here I use the limit of 29 dB, but essentially all the other users could have access to a greater data rate than because they're just closer to the OLT. And that, we believe, offers an opportunity to design a new generation of PONs where we would actually benefit from the extra capacity. And to represent in this way is that typically you would have a data rate that depends on the OLT to a new loss. And to really make that possible, you would typically implement multiple modulation format, not crazy one, moving from PAN4 to NRZ, change the error coding rate. You need to trade the efficiency of the coding rate with the distance. More efficient coding rate, more powerful coding rate generally has an impact on capacity. So it means you can go over longer distances, but then you have fewer bits transmitted. And on top of that, we could use probabilistic constellation shaping as a way to really bridge the full range of possibilities. In the future, there's still an open question that has been already partially addressed, which is, are we going to go coherent or not? As electronics reaches its limit, I mean, that limit will change over time, of course. There'll be progress there, but still the question will remain. If I want to go to higher capacities, what should I do? Of course, there's the possibility to go multi-wavelengths, which is always there. It comes with a significant extra cost generally. Or you can find a way to play with high-speed electronics. So there's a debate which comes with how much you believe technology is going to be ready on time. Either you believe electronics is going to do to serve what's needed, and you can stay with direct detection, and that's fine. Or you you think that only coherent will do the job, and then in this case you might afford to escape WDM as a way to increase further capacity. So I'm not saying that the debate is over. I think it's going to take time. If I just anticipate over to 10,000, 30, there's still expectations to change the game. But because in Nokia we are a maker of coherent, we know it's going to come at some point in time, even for optical access. So now I'm going to review some of the scenario where we believe PONs are going to need some upgrades. And there are and those have been partially already covered by the first presentation, but I'd be addressing them in the sense that where we see the most opportunities. So it will be about IoT, it will be about optical LANs, it will be about all flavors of fiber to the X, and it will be about mobile X hauling. I start with the last one. How can PON better serve the new generation of radio systems, starting with 5G and then moving to 6G? So we've learned from the deployment of even starting with 4G, we've learned that having a single fiber to connect the antenna to the rest of the network starts to be really difficult to manage. So if you come in a very dense area where you have multiple antennas, then you need to find a networking mechanism to aggregate the traffic coming in and out of those antennas. And PONs is attractive, especially where you have dense cell site deployment. So of course, this is going to replicate with 5G plus and with 6G. So yeah, PON really can be a game changer here. When you think about radio, what happens at the radio unit is that you digitize the waveform, and then the new trend has been to process digitally those waveform remotely. Starts to be remotely means in a distributed unit or even further in a central unit. Distributed unit is on the right of my chart, and CU, a central unit, on the left. The exactly where you're doing it is still being debated. The one that I'm presenting here, where PONs as a role to play, is already playing a role in aggregating multiple and the waveforms digitized for multiple antennas into one CUs after being post-processed in a DU. That's a reality today. What is coming because of different reasons, but essentially if you want massive MIMO to work, you need that change of split. You need to make sure that you post-process, even in the DU, the streams coming from multiple antennas. And then again, the PONs have a role to play with some changes. You'll hear some more about what we do in Nokia and in Bell Labs at the next conference, ECOC. But that's where we see their opportunities for PONs to be a game changer. Beyond 5G, there's going to be 6G. 6G is not going to be just about increasing capacity, but there will be some new forms of emphasis on expectations. Yes, there will be low latency. It was there for 5G, but determinism is going to be stronger. We need to cover more applications that are time critical. The trend towards moving away the data into generic IT infrastructure, what I'm calling cloudification, has been going on for so it's going to further expand. That has some consequences as well. And last but not least, the concern about sustainability, and now in a climate of war, even security, are going to be paramount in the design choice we're making about access networks. Talking about standards, what has been stabilized in the past months has been the 50G PONs. We've heard about that from a previous presentation already. I'm depicting here some of a typical layout of what transmitter receiver would look like. So an EML, electro-absorption based modulator with an SOA seems to be like the consensual view of where the industry is going. And it's going to be okay at that point in time. At the receiver, there's going to be some digital signal processing needed. It means some digitization first with an ADC. And so that's going to be the typical layout of 50G PON, even though there are some options still left available. We believe it's going to be very likely looking like this. We in Bell Labs are taken this exercise further, talking about demonstrating 100 gigabit flexible PON, showing that indeed we could cover a large variety of distribution of optical path loss. The opportunity I was talking to you in the beginning, where we typically we could be using PAM4 for the most capacitive links, but those that are at the smallest optical path loss as well. Whereas we would be moving to NRZ for the longest path. The way we would address each and every optical path loss would be by changing the coding rate, how strong the forward error correction coding would be. And in order to connect the path loss, the lower path loss to the high path loss, then we will use probabilistic constellation shaping in the same manner that we've been doing that for long haul systems. So we've demonstrated that in a trial where we've reached up to 85 gigabit per second net rate already. So that's really one big opportunity that we believe we should follow. So now, if I talk about other application scenarios, starting with a smart city. Smart city could be about cars, making sure that we worry about mobility. It's not just about that, but that's the example I'm shooting here. So when we talk about digitized cars, it can be because, of course, there's multimedia associated with that, broadband, multimedia, you name it, whatever you like in your car. But there's also, even without thinking of completely self-driving cars, we could be willing to control traffic in a much better way, in a secure and available communication network to supervise with the level of availability that we need. So that means building a completely new infrastructure based on 5G and 6G. And the reason why PONs would be a good candidate for that is that in PONs, there are some protocol extensions that allow some of the flows to be really tagged as priority traffic. It means low latency, but also very secure. You don't want to have your data lost in a situation where cars are being supervised by some network, by some remote supervisor that I'm showing on that graph. So it's something to follow as well. We believe there are some good opportunities there as well. And last, in the scenarios that where PON has a future, I'm going to talk about local area network. Not too much to say about it. I think there's some consensus that if you move to optics the traditional way of doing LANs, local area networks, you're saving on costs. You're building an infrastructure that lasts longer. So yeah, for airports, for hospital, hotel administration, whatever enterprise environment you have, yeah, optics is going to come one way or the other. But what is also striking is the appetite for introducing optics in factories. In factories, typically they talk about OT to describe. OT means operational technology as opposed to IT. So operational technology means any form of control or of industrial equipment in a factory, for example. And that you would need to do that in such a way that it's smoothly using the IT resources that you have anyways. The problem with OT, so think about control of robots, is that it comes with strict deterministic requirement. For example, for security reasons, you don't want to have the technician's head being chopped because you have some packet loss at some moment in time. So obviously, they have some very strong requirements that have been addressed with proprietary solution up to now. And PONs could be a way to support the new time-sensitive networking features that are meant precisely to have a good combination between the cloud and the control of robots with the requirements that are specific to the environment, which are shown in the bottom as examples. We want super low jitter and on top of latencies that are very stringent. And I was talking about packet loss. We also, of course, don't want data to be lost for this kind of application. So still some work to do, but room also for optics to be successful there. So overall, if I summarize the way Nokia sees the future of access by 2030, first of all, we don't believe that electronics is dead. There's still going to be a new generation of ADSL to covers with multi-gigabit connects, homes and buildings whenever it's there or whenever it makes sense. Optics most likely is going to compete with fixed wireless access, that is for sure. But optics is going to continue to evolve and it's going to break the 50 gigabit barrier for sure. It's going to continue to support mobile transport by offering low-cost solutions. We believe there's an opportunity to take it further to 100 gigabit by matching capacity, create margins wherever it makes sense, as well as serve Industry 4.0 by providing deterministic solutions. Thank you for your attention.
Thank you very much, Sebastian, for your presentation. So there are two questions for you. The first one from Junzu. I heard Sebastian mention PON to support 6G time-critical applications. My question is, do you think PON latency is sufficiently low support? Or if not, how to improve PON latency to meet these applications?
I would say it depends on the application you're considering. There's a lot of time-critical application in the list for example, in the list of standards. I think in the ETSI presentation, you've seen quite a lot of those. Each of them come with their own requirement. So some of them could be covered by a PON requirement, but I agree with you that a number of those are not going to be supported by PONs as they are today. It doesn't mean there's no extensions possible. We do believe there are extensions possible. I was talking about a paper that will be presented at ECOG by my colleagues, which actually works on that. There are some possibility to make PONs better cooperate with each other. And that's what you hear about. So no, I don't think PON latency is good enough, But yes, there are possibilities to take latencies to lower values than they are today.
Thank you. There is another question from Fabien Saliou. How current technologies could be adapted or simplified for the specific constraint of access networks?
Sorry, I missed that one. How current technology could be adapted? Um, I would say, if I consider current technology today, there are a lot of processing power that is devoted to functions that are not truly needed in access network, or at least to an extent which is not the same. I take, for example, half of the processing power in a DSP, or at least a large fraction, maybe not half, 1/3, comes from chromatic dispersion compensation. So it has some true advantages for PONs. Fabien, you mentioned the fact that when you move to 50G PON, you would like to stay in the 1.3 regions because of chromatic dispersion requirement. With coherent, of course, you alleviate everything related to that. But at the same time, we're talking about small distances. So it means that we can really remove a lot of the power consumption and the complexity associated with chromatic dispersion compensation associated with that. But overall, I would say we need to review all the different functions of the DSP and make sure that we make a cost-effective, cheap one. I don't have a better answer to that, except that we will be leveraging all the history in long-haul network, where a lot of those things are already very, very much integrated. Yes, there's still some challenges to make it really cheap as they need to be. But again, there will be maybe a 20-year history in long-haul network which we can leverage.
And I have also a question for you. Do you have an idea of the cost for the mobile transport network? You meant that there will be a low cost. So do you have an idea of the cost?
Don't know how to answer that question. Could give you only relative cost, but I am not sure what exactly you're referring
Okay.
to. So I know when you say low cost, it doesn't mean a lot, because if you don't give any order of magnitude, but it's like I should say cost effective, in a
Ah,
sense
okay.
that we believe there's going to ready to accept the cost.
So I think that's not a problem. We will answer that at the end of the webinar. We'll go with the next presentation. So the next presentation is François Lelarge. So François, I invite you to join stage. He's the CTO of Almae Technologies. He will present key enabling technologies, active components, and devices. So François, the stage is yours.
Thank you. Thank you for the invitation to present our activities, and in particular try to see how we can contribute to a new network. In this presentation, I would like first to introduce briefly Almae Technologies and demonstrate or introduce what kind of technology are available in Almae Technology as a chip supplier. Because as we discuss, for this 5G and 6G network, there will be some significant change in the network itself, but it impact a lot the expected performance from the chip performance. It's really important to keep in mind the overall context of 3.5 chip industry, because we have to work a lot in synergy between existing technology. So in particular, 100G transceiver developed for datacom and existing PON technology. Just a quick overview. Almae Technology was founded in 2016. It's a relatively young company, but Almae Technology is benefiting from a very strong technology on the indium phosphide processing, design, epitaxy processing, and testing. And this background is coming from different companies in the past, including France Telecom, Alcatel, and then Nokia. So we are like a spin-off of Free5 Lab to put the technology developed within Nokia on the market. As I said, it's a key point. The key point is to keep in mind the context and why we are developing indium phosphide chip. The worldwide demand is booming for a lot of different applications already mentioned by the previous speaker. Of course, the datacom and telecom market. But we already see the booming of LiDAR or consumer sensing. It means that for all chip supplier, there will be two challenges. Both be able to catch the market by a very significant industrial scaling. Because the numbers that we are supposed to deliver in the next years is really large as compared to what was done previously, even for datacom application. And on top of that, as mentioned by the previous speaker, we need to develop some technology breakthrough in order to be able to package such a very large number of chips. So we have a good microelectronics industry, but we believe that the industrial indium phosphide platform could be in the next year the real bottleneck for photonics. So just an illustration, but already mentioned that the number of optical transceiver and the budget amount are growing regularly and significantly every year, and in particular driven by the datacom industry and by the wireless demand. Now I would like to introduce the Almae industrial platform. So just a few words about our very basic roadmap. Almae Technology is a chip supplier, so we are fabricating Free5 chips for like lasers, SOA, integrated laser modulator. So basically, we develop first discrete chips that are mostly used in pluggable optics by our customer, and mostly for telecom datacom. And the next step will be to work on the advanced assembly of chips, in particular DFB chips with silicon photonic engine. For instance, if we want to go to a coherent solution. Our objective is to bring the best of indium phosphide chips to all market actors and quickly grow the industrial platform in Europe, free to operate both in Europe, US, and in Asia. In addition, we would like to develop the assembly of photonic chips, in particular based on passive alignment with silicon nitride SOI circuits for developing a highly automated, low-cost, high-volume integrated platform. Our main product up to now is a integrated laser modulator. Maybe just to explain rapidly, it means that we monolithically integrate on indium phosphide a laser section that gives a continuous wave emission at the wavelength of operation. Could be a CWDM, DWDM, whatever. Plus, we add an EAM, so an electro-absorption modulator, that will on which we'll apply different voltage in order for the EML to be ever transparent or absorbing. So then we will transform an electrical signal in an optical signal for fiber transmission. Just a brief overview of the EML process flow. We have different steps basically to integrate the to grow modulator-based AP, then integrate by budget technology the laser, define the grating, define the ridge waveguide, and bury the ridge waveguide. So this is also followed by standard metallization, interconnect metal thinning, and so on. And you can see on that figure the resulting period EML integrating the laser section with a modulator section. So everything is produced in Marcoussis. It's about 30 kilometers on south of Paris. And we have all epitaxy and processing tools to fabricate in volume EML. So it's a full 3-inch or 4-inch wafer clean room facilities. Now I would like to illustrate some key components that will be used potentially for 6G. From what we understood, in particular from the previous talk, what would be the main need? We need high-speed source, and the EML technology is already on the market for 100G per lane, using the PAM4 modulation format. We need high power EML for PON. We may need high power DFB for silicon photonic-based transceiver for coherent. And we need a technology that will be low cost and compatible with high volume component. Let's look at what is already existing on the market. So first is a 100G EML per lane. So it's basically based on a 50G EML combined with a PAM4 modulation format. So here you can see that LMA technology is can achieve a 40G modulation bandwidth, and that gives a full DR4 modules in O-band. So it's a key technology. They're mostly used for that. Datacom. For PON, we have developed a 15767 for the 10G PON. So it's either for XGS or a combo solution. Once again, all these chips have been developed and validated by our customer, and in particular here in case of S-Link. As mentioned by Fabien and Sébastien, the the next generation of PON will start by the 50G EML for PON. At the chips level, the requirements is highly challenging because they need something like 13 dBm of output power. And it's complex because it means that you need to find a very good compromise between all requirements. So including 50G modulation, low peak-to-peak voltage, high extinction ratio, and you have to avoid the modulator saturation. So in the model of Almae, we are developing with our customers some really specific, and we tune our technology to optimize the design. So this is illustrated here, where you can see that on the same wafer, we can evaluate and test different kind of EML to find the best compromise in between the absorption and the extinction ratio. And the results in the eye diagram that you can see that was done in collaboration with Huawei Munich is a demonstration of a 50G NRZ modulation, demonstrating the 13 dBm output power required. Most recently, we have developed another solution that you can see on the top image, where you have a laser section plus the modulator section, so it's a standard EML, plus a SOA section and a tilted output. So the tilted output is required because, as mentioned, the optical feedback in PON network are there. So we really need to have a tilted output to protect the EML SOA from any kind of feedback. What was demonstrated is that we can have a 50G response and modulation, and now be in the range of 15 dBm of output power. So we believe that this is a significant breakthrough, and that can support the demand from Orange, as described by Fabien, for instance. Maybe last point is about the laser technology that can be also used in a more simplest device, in particular by just using the DFB section. So in that case, we have developed in Almae both C-band and O-band high-power DFB, so able to deliver something like 100 milliwatts. And this kind of high-power DFB can be used for pumping Mach-Zehnder modulator for current solution, for instance. Can be also used for LiDAR and other application. What we believe is we need, if we go in that direction, to benefit from the best of both indium phosphide and silicon platform, we need to have a very efficient coupling between the indium phosphide chips and the SY or silicon-based waveguide. So in that case, it's why we have developed a very specific spot size converter on the indium phosphide chip, and we are working with partner developing some silicon nitride waveguide in order to have a very good coupling efficiency, a good overlap between the two modes. So we believe that this piece of technology that have been already demonstrated will be key in order to support any kind of change, major change in the technology. This is so this new kind of technology means that we have to be able to passively couple or indium phosphide chips with any silicon nitride, SY, waveguide. So this is a demonstration that is actually performed within our parent project, in which we have developed a specific SOA design that is efficiently coupled with a thick SY platform. So maybe to conclude, we have available indium phosphide platform already qualified for telecom and datacom product, both CWDM in O-band, DWDM in C-band. We have key building blocks for combining different section, like a small photonic integrated circuit. So, as discussed by the previous talk, I will let you conclude about which one of these device or combination of those will be used for the 6G. So thank you for your attention.
Thank you very much, Francois, for your presentation. So if you have any question, feel free to ask. I have one, there is one question from Gabriel Charlet. GFB is mentioned for coherence transponder. Usually for LH at least, tunable lasers are required. Here, this is for a different application.
It's a good point. Key point as we see is really to develop the technology for efficient coupling. This is why we believe at longer term we may use a gain chip like a reflective SOA coupled in a silicon nitride, for instance, and which we can have a tunability on silicon and then combined with silicon-based modulator that can be also used lithium neobat or whatever. So the point is to make sure that all indium phosphide discrete chips will be available to support any kind of new device.
I have a question for you. So you talked about a continuous laser. Why is it more interesting to have a continuous laser?
No, in a EML, I was, maybe you're talking about high power DFB.
Yes.
For the let's say, if you want to keep the modulation on indium phosphide, of course, you will move to EML or DML. But there are a lot of people who would like to rely maybe more on the modulation on the silicon chips. So in that case, they want a high power DFB because high power source does not exist on silicon platform. So you have to integrate CVM or to couple the high power DFB in order to pump different, a large number of silicon-based modulator, for instance. So in that case, you don't want to have a modulation on indium phosphide. You just need a high power, and then you will do the job with the silicon.
Oh, okay. Thank you very much.
Okay.
So are there any questions for all the speakers? Feel free to ask if you have one. And if you don't have any questions, so I encourage you to ask them, and if not, we will end the webinar. So we will wait a little bit. I invite all the speakers to join us on the scene. So Sébastien Bigot, Fabienne, and Gabriel. So there is no question. I think all of it was clear. Okay, so thank you very much. Thanks to all the speaker for your intervention, and thank you to all the participants. So I think it was a really good webinar, and I hope I will see you for next one. So thank you very much, and goodbye.
Thank you.
Thanks.
Goodbye.
Bye.
Bye.